Okay, this is 8-3, inverse trig triangles, and then we'll talk about radians on the next page. So inverse trig triangles are essentially doing inverse trig without a calculator. So this is something that's on our curriculum for sure, and we'll talk about sort of, essentially this is useful because we don't need a calculator to do this, but also when we're given a value like sine is equal to 1/2, 1/2, then we can find what cosine of that angle is without doing any calculator work. So what I'll preface this lesson with is that we will be using it's super important that we remember our unit circle, not unit circle. What I'm trying to say is special right triangles. Special right triangles are going to come up like a bunch today. So I'm just going to draw it right here are two different special right triangles, including their angles. So a 45-45-90 has a 45-degree angle, a 45-degree angle, and a 90-degree angle, of course. The side lengths for this triangle, if we were to make it really small, the side lengths would be 1, 1, and then root 2. So remember how we have not root x, root 2. Remember how on the 45-45-90 triangle we had x, x, and x root 2? Well, I'm just taking out the x because we're just looking at the proportions of this unit circle, this special right triangle. Keep saying that. So on this triangle, this is a 45-45-90 triangle with 1, 1, and root 2. And of course those can grow and shrink depending on which side lengths you're changing. So we could have 2, 2, and 2 root 2. That also is fine, but I'm just drawing the most simple one. I'm also going to draw 30-60-90 with its 90 degree here, 60 actually, 60 here and 30 here. And those placements are important. It's pretty easy to tell when you draw one that one of those angles is smaller than the other one, and that one's going to be the 30 degree, but just be careful as you do that. So on this 30-60-90, remember we had x on the shortest side, so we'll just label that 1. And then the longest side, the hypotenuse should be double that, which is 2 in this case. And then the other side is the square root of 3. Normally it's x times the square root of 3, but this triangle has 1 as its x value. So these are the proportions. So we'll be using these a ton. I would recommend writing these on there so that you have them. When we're doing these kinds of problems, what they'll give you is the value of an unknown angle, right? Because this is inverse trig and the angle is unknown. So it says sine of theta is equal to 1/2. And theta is between 0 and 90. So we'll follow the steps over here. First it says decide which quadrant you should be drawing in using the given range of angles. So I will explain what I mean by that here. When we're thinking about an angle between 0 and 90, and we're looking at a coordinate plane, what we're imagining is a circle like this, and angles within that circle starting here. So this is a 90-degree angle right here. So this is 0 degrees, this is 90 degrees, this is 180, this is 180 plus 90? 270 degrees, and then 360 wraps back around to be at the same place as 0 degrees. So essentially, we're deciding, it will tell us which quadrant we're supposed to be in. So for this example, it says between 0 and 90 degrees, which makes it in this quadrant of the graph. So I will erase my 90-degree mark there because I don't need it, but I will highlight the quadrant that I should be in here. Between 0 and 90 degrees is there, and that might change depending on what numbers they give you. So we'll do more examples of that. But that's the quadrant we're going to draw a triangle in. And I say that because I haven't explained that yet. What we're doing with this inverse trig without a calculator is we're going to draw a triangle and work backwards. So we have the value of sine of theta, and we're going to draw a triangle that matches those values and then determine what theta is. So then our next step just says the reference angle will always be touching the origin. So theta, the one that we're trying to find, will be on the origin. This is a little bit like when we drew triangles inside of a unit circle. Next step is we use trig definitions to decide what side lengths your triangle must have. So we have that sine of theta is equal to 1/2. But the trig definition says that sine is equal to opposite over hypotenuse. So the opposite side must be 1 and the hypotenuse must be 2. When we draw our triangle, I'm going to draw a triangle with the reference angle on the origin, and then it goes straight down so that that's the 90-degree angle. So here's theta, and from theta I need to find the opposite side and label it 1, and the hypotenuse and label it 2. So there's my triangle. I'm not sure what this third side is yet, but we'll get there. So we've drawn a triangle now that matches this definition, right? If we were to find sine of this angle, we would get 1 over 2 because it's opposite over hypotenuse. So next we have compare the triangle to the special right triangles and use that information to determine the reference angle. So we are comparing this triangle, not in shape, but in numbers, right, to one of these two triangles. And I want to bring your attention to the fact that the only triangle that this one could be is a 30, 60, 90, because we have matching side lengths. We have a 1 and a 2 side length. And that doesn't work for the 45, 45, 90. We have 1 and root 2, but it does work for this one, which means that this angle that we're looking at should be across from the 1, which is a 30-degree, making myself sick. The angle here should be 30 degrees, because that's what angle matches this unit circle triangle. Sorry, I keep saying that. Special right triangle. That angle has to be the 30 degree. If it were the 60 degree, then this number would be different. Hopefully that makes a little bit of sense. Using this information, though, we can fill in the third side of the triangle. This third side has to be root 3. And I know that just because of comparing it to my special right triangle here in the corner. And then we can use this information to find what cosine of theta is and what tangent of theta is. Fractions, right? So cosine is adjacent over hypotenuse. So that's going to be this side. I'll just write my little letters right here. It'll be adjacent over hypotenuse, so it'll be root 3 over 2. Tangent of theta is opposite over adjacent, which is 1 over root 3 for that one. And then we already know that theta has to be 30 degrees. So essentially this is what we're doing. We're drawing a triangle, matching it to a special right triangle, filling in the missing information, and then finding the other trig functions inside the triangle. That's the short version. So we're going to try a couple of examples here. First, we have this, number 1 says sine of theta, sine of our reference angle, is equal to negative root 3 over 2. So this might seem strange to you if you thought ahead a couple of steps. Negative, we're not usually allowed to have negative lengths. But on these kinds of triangles, we essentially are thinking about where it is on the coordinate plane, not how long it is. So we'll get to that in just a second, but it says the reference angle is between 270 and 360. So on our little map here, we are looking at 270 to 360, which is this bottom right-hand corner of our coordinate plane. So this corner is where we're going to be focusing. I'm going to draw a triangle here. Ignore the proportions of my triangle. What we're really going to focus on is actually the side lengths. Whoops. There we go. This is our reference angle. It's always the one touching the origin. And then we have that sine is negative root 3 over 2. So sine is opposite over hypotenuse. So the opposite side should be negative root 3. So see how we're going down from the x-axis? That makes that value negative. Hypotenuses are always positive, no matter where they are in these triangles. Hopefully, yeah, that helps. So negative root 3 is referring to the fact that it's below the x-axis, so we're going down on the y-axis. And hypotenuses are always positive. So again, comparing this triangle to a special right triangle here, we see that we have a root 3, so that's most likely only this one. It would be really hard to have a root 3 that goes in a 45, 45, 90. Ignore that it's negative, we're looking just at proportions. So what side we're missing here is the side that's 1. So that's the third side there. And using that information, the angle across from the root 3 side is the 60-degree angle in this triangle. See that? Those things are across from each other. So that reference angle has to be 60 degrees. Our only options were 60 and 30 because of the side lengths, and it's 60 because it's across from a root 3 side. And then we can use that information to find tangent and cosine as well. So tangent is opposite over adjacent. I'll write my little a right there. So tangent would be negative root 3 over 1, opposite over adjacent. And then cosine is adjacent over hypotenuse, so that's 1 over 2. Good, and that's all. So let's try number 2 now. This one says theta is between 90 and 180, so I'll let you look back at your reference there, but that's this quadrant. 90 to 180 is that quadrant. I'll draw a triangle. Here's my reference angle. And it says cosine, cosine is adjacent over hypotenuse. So adjacent is this side, so it'll be negative root 2 right there, and 2 for the hypotenuse. Okay, I was just double checking my work there. I think that there's a typo on that one actually. That should be root 3. Or maybe I'm doing it wrong. Yes. Okay, back up for a second here. Okay, we're okay so far, right? So adjacent and hypotenuse, we're here. My notes are wrong on this one, by the way, the one that is uploaded. So we have a root 2 and a 2 going on here, which I will note does not match either of these, right? The one that has a root 2 is the 45, 45, 90, and the one that's the 2 is the 30, 60, 90. So I will point out to you here that remember our proportions here are like x, 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 and x root 2. So in fact, it does actually match the 45, 45, 90. If we're thinking about these two sides as root 2, and this as 2, because what is root 2 times root 2? This is our x, and this is our root 2 from our special right triangle. That equals just normal 2. So these two sides will match for our 45, 45, 90, and then this side is going to be this side times root 2, which actually does work in this problem. So this is now our triangle, and that's perfectly good. Notice that our negative is here because we're going back on the x-axis, but positive on the y-axis, so this is still positive. And this is the opposite side. On 45, 45, 90 triangles, the only option is 45. So we don't even have to think about that much. As long as we know that it's a 45, 45, 90, we know that this is 45 degrees, because the reference angle is not going to be the 90-degree angle. And then we have sine and tangent to find. Sine is opposite over hypotenuse, so that's like root 2 over 2 again. What are we given that? We're given cosine, I see. But that's positive root 2 over 2, so it's slightly different. And then tangent is opposite over adjacent. So we might simplify this a little bit, because we have root 2 over negative root 2. That's just negative 1 if we simplify. And then we already know what theta is. That's 45 degrees. One last problem here before we go on to talking about radians a little bit. Tangent is 1, it says. So it's between 0 and 90 is what we're working with here. So I'm going to just highlight my quadrant really quickly and then draw a triangle. Triangle. Here's my reference angle. It says tangent is 1. So this is not a fraction, which it probably feels very confusing. But I want you to notice that 1 is the same thing as 1 over 1, or literally any same number over the same number, right? We're going to use 1 over a 1. It doesn't actually matter which one you use because the answer will still be the same. As long as tangent is 1, then you're solid, right? So if we instead use 1 over 1, tangent is opposite over adjacent, so this means both of these sides are 1. And that triangle matches, that triangle matches this triangle again, 1, 1, and the third side needs to be root 2. So this again is a 45, 45, 90 triangle, which means the theta is 45 degrees. Cosine of this triangle is going to be adjacent over hypotenuse, which is 1 over root 2. Sine of this angle is going to be opposite over adjacent, which is actually the same thing as well. And that gives us the other values there. I know this stuff is like sort of confusing, and I'm aware of that. So let me know if you have any questions or concerns about this. Essentially, if you make your triangle match one of the special right triangles, you're probably on the right track. Figuring out things like this where the proportions are the same makes it a little bit more difficult, but those will pop up sometimes, so being aware of them is good. Okay, so let's talk about radians a little bit. Radians is not super connected to this, although it does deal with fractions. So we're going to just talk about radians here. This page talks about how like degrees is actually not the only way to measure angles. And in a calculator, calculators have two modes. One of them says radians and the other one says degrees. And in class we had people that had their calculators on the wrong mode and were getting wrong answers for when they plugged in trig functions, and that's because the calculator was thinking they were measuring in radians instead of degrees. So so that might be what's wrong with your calculator if you're having issues, because the radians and degrees are measured completely differently. Have you ever thought about how sort of degrees is just like the amount of degrees in a circle could really have been anything. And this is like, there's a typo in here. It's like everything about how a year has 365 days and a circle has 365 days. I meant 360 degrees. But basically that measurement, 360 degrees, came from ancient observers watching the constellations rotate in the sky over the course of a year and sort of guessing about how many days it took. 360 was wrong, obviously, and 365 is closer, but really it's like 365 and a quarter, right? Because we have leap years every 4 years. So 360 days is actually like 360 degrees, is really kind of arbitrary. It's just a fraction that we're dealing with in a circle. So if we had, like, for example, lived on Mars, a circle would have 680 degrees instead of 360. So that's something to, like, sort of think about when you're not sleeping or something. That it totally does not matter what, like, how many degrees are in a circle. Everything would have worked just normally if we had 680 degrees in a circle. Like, we would have to adjust our trig functions a little bit, but it would have worked the same. Radians is like a more recent way of measuring angles, and some people consider it like the more mathematical way to do it, because it's not as arbitrary, essentially. So the fractions, and yes, they are fractions that we use, are based on the circumference of a circle with a radius of 1. Essentially, we're back to the unit circle. We talked about this the first lesson of this unit, and we'll talk about this unit today, and also like the next lesson that we do. A unit circle is just a circle with a radius of 1. So the circumference of a circle you find by plugging in the radius to this this equation. Circumference is pi times 2 times the radius. So the circumference of this circle would be pi times 2 times 1 because of the radius of 1, which is just 2 pi. So we are talking about a circumference of a circle, of the unit circle, as being 2 pi. So to measure angles, we just say how much out of 2 pi that angle is. So the whole thing, if we're going all the way around, maybe I should use my pointer here. If we're going all the way around, that's 2 pi. 2 pi is essentially the same thing as 360 degrees. That's all the way around the circle, because that's the total circumference. And everything in the middle is just based on that. So if the whole thing is 2 pi, then half of the way, which normally we call 180 degrees, half of the way is just pi, because that's half of 2 pi, right? So we'll say 2 pi is over here, that's the whole way around. 1 pi is half of the way around. Like half, if we half that again and get this 90 degree angle, it's just half of pi, because we're dividing in half again. So if we use that measurement, if we have, let me get my pointer, if we have 1/2 pi, 2/2 pi, 3/2 pi, then this is 3 pi halves there. So I realize that fractions are often not a strong suit, and I get that. So radians are often like we're doing fractions and degrees at the same time, which is like annoying. I get it, but if we start with the idea that the whole thing is 2 pi, then we can just divide it into all these pieces that we know how much, right? 2 pi divided by 4 is pi halves, which is where we get this value here. If we divide that in half, we get pi fourths for this 45 degree angle there. And then we can count pi fourths. Each pi fourth is going to be one more pi fourth, right? So we have one pi fourth, 2 pi fourths is the same thing as pi halves, and then 3 pi fourths, 3 pi fourths. That's 3 pi fourths. 4 pi fourths is the same thing as pi, and then 5 pi fourths goes here. 5 pi fourths. 6 pi fourths is the same thing as 3 pi halves, and then 7 pi fourths is there, and then 8 pi fourths. 8 divided by 2 is 2, so that's just the same thing as 2 pi. So that's us all dividing all of that into halves and quarters and eighths of this circle, right? These other lines are not dividing in half again. Notice that this is like not in the middle of those two. This is actually dividing this much in threes. So this is a 30 degree angle normally. So this is 30 degrees, this is 60 degrees, this is 90 degrees up there. So when we have a 30 degree, what we're doing is dividing this value, pi halves, by, pi halves divided by 3 is what we're doing there, which ends up being pi sixths, because we're already at pi divided by 2. If we divide it by 3 again, we get pi sixths. So now we can count by pi sixths as we go around the circle, because each of these values is going to be a pi sixth. So we have 1 pi sixth, 2 pi sixths, 3 pi sixths is the same thing as pi halves, 4 pi sixths, 5 pi sixths, 6 pi sixths, same thing as pi, 7 pi sixths, 8 pi sixths, 9 pi sixths, which is the same thing as 3 halves, and then we have 10 and 11 and 12 pi sixths. So I will just write those values in. So we have pi sixths, 2 pi sixths, actually can be reduced to pi thirds, pi over 3. So I'll leave that conversion there just in case you're counting like me. 2, 3 pi, 4 pi 6, 5 pi 6. This can be reduced as well to be 2 pi thirds. 5 pi 6, 6 pi 6, 7 pi 6 goes here. 8 pi 6 can be reduced to being 4 pi thirds. 8, 9 pi 10 pi 6 is the same thing as 5 pi thirds. And then 11 pi sixths is the last one that we have. So these are our radian measurements for our common degrees. So I will write the degrees that they're equivalent to in here, maybe in a different color. So this is 30 degrees, this is 45, this is 60, this is 90. This is 90 plus 30, so 120 degrees. This is 135 degrees. This is 150 degrees. This is 180. This is 270 degrees. We'll say this is 360. 180. Plus 30 is 210 degrees, and this is 225. Yep. And this is 240 degrees. I think, yeah, plus 30 more is 300 degrees. That's 315 degrees, and this is 330 degrees. Okay, fantastic. So there's all of our degree measurements. And if you ever need this, you can actually Google the unit circle and it will come up. There's a lot of other information on the unit circle that you might not need quite yet, but or you can just Google radians as well. That is fantastic as well. So that's what radians are. Essentially, they're just a different way to measure degrees, and it's fractions, and it has to do with pi. So a little bit less arbitrary than just 360, but also kind of difficult because it's fractions. So the conversion rate between degrees and radians is also useful to know in case you need to convert from one to the other. So the way that you do that is just multiplying by, well, in this direction, we have to multiply by pi over 180. From degrees to radians, you multiply by pi over 180. So if you have 90 degrees and multiplying by pi over 180 gives you 90 pi over 180, 90 out of 180 is a half, right? So that's ends up being the same thing as pi halves, which is a radian measurement, right? So 72, and this is of course without looking at our circle that we just did, which has the answer on it, but feel free. So 72 degrees goes into 180, well, 72 degrees, we'll look at this, because why not? Oh, because 72 is not on there. That's why. So 72 degrees, if we reduce that, it gives us like 2 goes into both. Oh, 3 goes into both. 1 second, I'm doing math. 72 divided by 3 is 24. 180 divided by 3 is 4. 80 divided by 3 is 50, right? 60, okay. 60, which also reduces because 4 goes into both of those things. So that gives us, actually 6 goes into both of them. So 4 pi over 10, which then actually 2 goes into both of those. So 2 pi out of 5, 2 pi fifths. Lots of reducing fraction there, but hopefully you can figure that part out. Going the other direction, so if we're going from radians to degrees, we have to multiply by the opposite of this, so 180 out of pi instead. So doing that, 3 pi times 180 divided by 4 times pi, so I just multiplied by 180 over pi. The pi's cancel. The 4 and the rest I recommend doing with the calculator. So you do 3 times 180 on the top, makes 540. Don't have room for this. 540 out of 4, which gives you 135 degrees. That was the one that's on our chart there, though. Do the same thing for this one. We have 5 pi times 180 out of 6 pi, so the pi's cancel, and we have 5 times 180 is 900 over 6, which is 150 degrees. Here we go. Yeah, so that's all I have for you today. I know this stuff is new and different, so please let me know if you have any questions, or join the Zoom on Fridays, because I'm happy to help.